Alrighty. Yeah, so I normally like to try to begin with a brief recap of last time. That also lets people trickle in who might be running a little late, and then move on to the new discussion. So last time we discussed what is a snark and how they're designed. So these are, as a reminder, basically the snarks are probably the reason most of you are here. They're the sorts of proof systems that kind of are most useful in a lot of cryptographic applications, especially to blockchains. The S means that the proofs are short and fast to verify. The N means that the proofs can just be written down and like posted to the blockchain for anyone in the world to check whenever they want to. And then ARK stands for argument of knowledge. This roughly says that unless the prover can break some crypto system, it can't manage to find a convincing proof of any false statement. So in a lot of blockchain applications, for example, the prover is claiming to know a whole bunch of transactions that have all been properly signed, such that the signatures do pass verification, thereby establishing that the party that owns the private key for the wallet or address or what have you that's authorizing the transaction indeed signs and thereby authorize the transaction. And the ARK means that unless the cheating prover can break some crypto system, in order to find a convincing proof of the claim, the prover must actually know what it claims to know. In this case, a bunch of valid blockchain transactions that have all been signed properly. And then we discussed how snarks are designed, and with just some minor caveats, this typically works in sort of a three-step process. So first you design something called a polynomial IOP, and we talked last time about what that is. And then you design separately a cryptographic object called a polynomial commitment scheme. And you can just put those two together in a straightforward way to get a succinct interactive argument. And then typically that interactive argument is public coin, which means you can apply the Fiat-Shamir transformation to render it non-interactive and thereby get a snark. And so I won't repeat the details today of what is a polynomial IOP and what is a polynomial commitment, but you will notice the word polynomial appears in both. And in both cases, this literally refers to the kind of polynomial you learned about probably in middle school. So something like, 1 plus x squared plus 3x to the fifth, so this sort of polynomial. Sometimes for many snarks, what are relevant are not so much univariate polynomials as multivariate ones, but at any rate, polynomials are absolutely the key to the design of efficient snarks. And today we're going to see our first hints of why they are indeed so useful. Because if you're encountering this theory for the first time, that might be sort of strange, like why, what do polynomials have to do with, proving things to the blockchain? So that should become much clearer today. So today we're going to see a stark demonstration of the power of randomness, especially when combined with polynomials. So that's the main topic for today. So we're going to see a very cool protocol. It's not actually going to involve a prover, but it's going to involve polynomials and randomness to achieve vastly better performance than what's possible without them. But let me just pause here and see if anyone wants to ask a question following that recap and that sentence or two about what we're going to discuss today. Okay. So before I dive into this cool protocol that uses randomness and polynomials, I think it'll be helpful to briefly discuss finite fields because, as we'll see, the polynomials that snarks like to use are defined over finite fields. And there is very little you need to know about finite fields. But so let's discuss what that is right now, what you need to know. Let's first just talk about fields in general, forget the word finite. So a field is a set, it's a set of elements. If you want to have a specific example or two in mind, think of the real numbers. They are our field. So are the complex numbers. So are the rational numbers. I guess the set of all like invertible matrices, n by n matrices, over any other field, say the real numbers, is also a field. So these are examples. Yeah, so the set of elements for like the real numbers is like, the uncountably infinite set of all real numbers. For the rational numbers, it's all rational numbers, so on and so forth. Okay, so what do we require of our set, our set of elements? We basically require that you can add, subtract, multiply, and divide any two field elements, with the caveat that you cannot divide by 0. Okay. So that's it. I could really just stop here and say, hey, a field is any set of elements such that you can add, subtract, multiply, and divide any two field elements, with the caveat that you can't divide by 0. But I think some of you probably would like me to say a little bit more than that, so I will. So in a little more detail, there are the following properties that are required to be satisfied by any field. So the field comes equipped with two operations, and we call those operations addition and multiplication. So I'll just denote those plus and times. Okay, so we require that there is an so-called additive identity element, which we naturally denote by 0. And that means that for any field element A, so this notation is for any A in the field. So this bold F is how I denote field, and this symbol means is an element of. A plus 0 equals A. Okay, so there's this element that we call 0, such that adding 0 to A results in just A itself. Also, this is called the additive identity element. Similarly, there is a multiplicative identity element, which we call 1. And that's what it sounds like for any field element. If you multiply it by 1, you get out the same thing you started with. And then, of course, if you take any two field elements and multiply them, you better get out another field element. So that another way of saying that is that the field is closed under multiplication, and the same has to hold for additions. So for any two field elements, A and B, A times B is also in the field, and A plus B is also in the field. And then finally, let's talk about subtraction and division. So for any field element A, there is another field element which I will suggestively denote by minus A, such that if you add minus A to A, you get out 0. So under this, once the field has this property, you could define subtraction via addition to say that A minus B equals A plus minus B. Okay, so this is all pretty pedantic, right? Like you might actually get confused, feel like what I'm saying is like super obvious or trivial or something because I'm choosing notation that like directly corresponds to the notation you're used to seeing when we talk about the fields you're used to seeing, which is typically is like the real numbers or the rationals or even complex numbers. But yeah, I guess the point is, I said that the field comes with 2 operations, addition and multiplication. I didn't say it comes with subtraction. I'm defining subtraction in terms of addition using the property that, we require every field element to have an additive inverse. Minus A. So if what I'm saying just kind of seems very pedantic, why am I spending time on it? Feel free to not worry too much about it. And just, we'll talk in more detail shortly about the actual fields that come up in snarks. But for now, just think of everything as the real numbers, and addition and subtraction are what you're used to, and multiplication and division are what you're used to, and that's just fine. Okay, so just 2 more properties we need. So for any field element A, there is another field element. I'll call it A inverse, the multiplicative inverse of A, such that A times A inverse equals 1. But I should have clarified this requires A to be non-zero, because just as over the fields you're used to, you cannot multiply 0 by anything and get out 1. So we certainly can't require that, or we wouldn't really have any interesting fields. So this is formalizing the property that you can divide by any non-zero field element. Right, so that is, I can define A divided by B if B does not equal 0 to be A times this multiplicative inverse of B. Okay. So I think is that everything? I think that's everything required of a field. So yeah, it's these bullet points are just formalizing the requirements that you can take any 2 field elements and you can add, subtract, multiply, and divide them. Of course, you can't divide by 0. Okay, so that is a field. I will shortly talk about finite fields. But let me pause and see if anyone wants to ask any questions about what is a field. No questions? Okay. Very good.
Just a question about these other properties like associativity, or I don't know if that's relevant or important.
So all of so a field in general is not required to satisfy associativity. Is it? Sorry, let me think. Certainly not commutativity. Associativity probably does satisfy associativity. I don't know. Yeah, I guess it's not going to matter much if I don't have the answer cached. So the finite fields we're going to work over, certainly addition and multiplication will be associative. Yeah, okay. It's possible, I need to review my abstract algebra to see if I should be insisting that the multiplication and addition operations are associative, or if that just is sort of automatic. But yeah, like the invertible matrices, certainly like multiplication of matrices is not commutative, for example. So like A times B as matrices does not necessarily equal B times A. So that means for sure, like there are fields where multiplication is not commutative. So mult is not commutative. And that's fine, it's still a field. Multiplication and addition are always associative. Yeah, I don't know if I don't have cache whether I have to require that or not. Anyways, so it's not going to come up in the study group, and I'm just revealing how long it's been since I've thought seriously about algebra. Is that enough of an answer for now?
No, I think that answers the question. Thanks.
Okay. Any other questions?
If I can jump in, I think that like the field requires that both of the groups are abelian, so it will be associative and also commutative.
Well, I think invertible matrices are a field, but the multiplication is not commutative, right? Or
well, I assume they are not always a field. I think that the matrices would have to be like regular.
Oh.
Or have the same dimensions.
Yeah. Sorry, n by n. So that the n by n matrices.
Yeah.
And I think they I thought they are a field, but they don't necessarily commute multiplicatively. Okay, well maybe I'll suggest that I write something in the chat afterwards. Take out my abstract algebra book and look at the definition of a field. And see if it requires anything about associativity or commutativity in there. Fortunately for snarks, invertible matrices are not going to come up, and we just exclusively work over finite fields, and they, certainly the prime fields, which are the most important, are both associative and commutative, which is why I happily forgot everything I used to know from abstract algebra, since they're just the objects that we work with in Snark design are pretty simple in the scheme of all possible algebraic objects out there. Okay, so after embarrassing myself with the questions, does anyone want to ask anything else? Great. Thanks for the questions and for helping out too when I botch them. Okay, finite fields. So finite fields are just what they sound like. They're fields where the underlying set of elements is finite. And so the main example to keep in mind is the integers modulo p for any prime p. So this is always a field, always a finite field. And in case you haven't encountered the notion of modular arithmetic here, what this means is that you sort of replace any integer with its remainder when you divide it by p. So for example, the integers modulo the prime 7 would just be 0, 1, 2, 3, 4, 5, 6. Right, and you'd have like 7 is congruent to 0 mod 7, 8 is congruent to 1 mod 7, 9 is congruent to 2 mod 7. Do a quick larger example, I guess like 18 would be congruent to 4 mod 7, right? Because the remainder when you divide 18 by 7 is 4, right? 18 is 14 plus 4. Mod 7. So that's what modular arithmetic is. So, and if you're like a C programmer or a Python programmer, this is like, to reduce 18 modulo 7, you'd write like 18% 7 and it would return 4. Okay. So whenever P is prime, the integers modulo P is a field. And when P is not a prime power, so when P is composite, the integers modulo P are not a field. And the key property that gets lost when you work modulo a composite number is multiplicative inverses. That is the ability to divide by any non-zero field element. Okay, so let's see a quick example. I guess let me work mod 5 now. So I'm going to write out the multiplicative inverse of each number mod 5, other than, of course, 0, which has no multiplicative inverse. So the multiplicative inverse of 1 is always 1, because 1 times 1 equals 1. The multiplicative inverse of 2 mod 5 would be 3, because 2 times 3 is 6, which is congruent to 1 modulo 5. The multiplicative inverse of 3 then would be 2. And then sort of by process of elimination, the multiplicative inverse of 4 better be 4, which you can check it is. So 4 times 4 is 16, which is congruent to 1 modulo 5. Okay, but if we thought about the integers modulo 6, I think it should be that if you take any number that's not co-prime to 6, it won't have a multiplicative inverse, I think. So like, for example, let's take 3. So it turns out there's no number you can multiply 3 by to get something that's congruent to 1 mod 6. So like, for example, so 3 times 0 certainly doesn't work. That spits out 0. That's not congruent to 1 mod 6. 3 times 1 is 3. 3 times 2 is 6, which is congruent to 0 mod 6. 3 times 3 is 9, which is congruent to 3 mod 6. And so on and so forth. Equals 15, which should be congruent to 3 mod 6, right? So I went through the whole like multiplication table with 3 being one of the 2 elements in the multiplication, and 1 never came out. So this means like there is no multiplicative inverse of 3 mod 6, so the integers mod 6 are not a field. Okay, and yeah, the exact failure issue here was that 3 is not co-prime to 6. So if you were working mod a prime, everything is co-prime to that prime. And so, this sort of situation where there's no multiplicative inverse of some element of the set just doesn't arise if you work modulo a prime. And that is why the integers modulo a prime are always a field. That is all you need to know for this entire study group about finite fields. So I will pause here, see if anyone wants to ask another question and embarrass me again. Okay. So as we'll see today, kind of the security properties of snarks, or in general protocols that use finite fields, tends to fall with the size of the field. So if you want like cryptographically strong security, you generally want your field to be pretty big. If it's not, you can work over smaller fields, and then kind of you have to repeat the protocol or parts of the protocol many times to drive the probability that the attacker kind of gets lucky lower. But the sorts of fields people tend to work over, examples that come up a lot, so 2 to the 127 minus 1 is a prime. It's like a very nice structured prime. So like reducing numbers modulo this prime is like very fast. Maybe one of the most popular fields in practice now is a little bit small. So when you use it, you do have to do things like repeat parts of the protocol many times. It is called the Goldilocks prime, 2 to the 64 minus 2 to the 32 plus 1. Let's see. Well, maybe I'll stop here. So yeah, these are the sorts of primes people work over. Sometimes they go even higher. So if your snark is going to use elliptic curve cryptography, you typically are going to have to work over a field of size at least 2 to the 256, sometimes more. So basically, I don't know. So this is way more in the weeds. If what I'm about to say doesn't make sense to you, don't worry about it. If you need an elliptic curve group, and you don't require it to be pairing friendly, so non-pairing friendly, you can wind up working over a field of about this size and have what's called 128 bits of security. If you do want pairings, you have to go even higher. Maybe 12.3, maybe fields of size about 2 to the 381 for pairing friendly fields. Okay, so the summary is like, the fields people work over, they're not like size 5. They're much bigger than that. So 2 to the 64-ish is on the smaller ends. People might go even lower than that, but again, the lower they go, the more they have to repeat certain parts of the protocol to get adequate security. They can go as high as, almost 400 bits. Okay, so just something to keep in mind as you sort of try to make everything concrete in your head. Okay, so please jump in at any time with questions. But if people are happy so far, then let us start seeing the power of randomness. Okay, so I want to discuss just a particular problem. It's a really natural and fundamental problem in computer science, but I'm bringing it up just to display the power of randomness, again, especially when combined with polynomials. Here's the problem. So we have two parties, Alice and Bob. They each have a vector. Think of the vector as very long. So it's they're going to be vectors of field elements. So here F is some finite field, bold F. If you want to make things concrete, say it's like integers mod 2 to the 127 minus 1, just to have an example. And let's say n is, I don't know, 1 trillion. 1 trillion is about 2 to the 40. Okay, so they just have each is holding 1 trillion field elements. Now this would be many terabytes of data. But what they want to know is, they want to know, are they holding the same vector? So determine whether X and Y are the same vector. Okay, and what they'd like to do this while minimizing the amount of data they send each other. So in general, maybe Alice, can send some message to Bob and he'll respond with some other message, and Alice will respond to that message, and, so on and so forth. And the amount of data they send each other is just like the sum of the lengths of all the messages. So that is also called the communication cost. So they want to determine, do they have the same vector while minimizing communication. This sort of problem actually comes up in the real world. Like, you could imagine Alice and Bob both like downloaded some giant file from some central repository, and they want to make sure that there were no errors in their downloads. That is, they both downloaded the same thing or something. And if the communication between them is like more expensive than the communication between them and each of them individually in the central server, they really don't want to just, have Alice like send her file to Bob. Firstly, there might be additional errors introduced in sending such a large file to Bob. And secondly, it's just expensive to send all that information from Alice to Bob, maybe way more expensive than it was for Alice to download it from the central server or something. Maybe central server is Netflix. Alice and Bob want to make sure they watch the same movie. It really is worse for you to like email a movie to your friend than it was for you to just download it from Netflix directly. So this sort of problem does come up in the real world. People do care about it. And unfortunately, if they want to know for certain whether X equals Y, Was it X and Y? I'd call it X and Y. Okay. Let me change the name of the vectors to A and B. For reasons that I'll try to remember to mention later. Okay, so if they want to determine whether X equals Y, A equals B, they actually can't do better than just allocating her whole vector to Bob. Like there's just nothing non-trivial they can do. Right? So Alice could send her vector to Bob, and Bob can just, check entry by entry, is it equal to his vector? And if so, he says, well, they're equal. And if not, he says, well, they're not equal. And you just can't do better than that. So we're not going to prove that statement, but it's sort of intuitively very plausible. If Alice were to send like every entry of her vector to Bob except the last entry, well, maybe A and B agree at every entry except the last entry, and then the very entry Alice submitted is exactly the one where they differ. And then so according to all the information Alice sent to Bob, they look like they're the same vector, but in fact they're not, because like the one thing Alice left out is exactly where they differ, right? So you can actually prove, and we won't, that Alice really does have to just send her whole vector to Bob. You can't do anything better than that. There's sort of trivial variations you could do, like Alice could send the first half of her vector to Bob, and Bob could send the second half of his vector to Alice. So you don't have to have all the communication go from Alice to Bob. You can kind of split it between them, but nonetheless, in total, they ultimately have to exchange all n field elements between them. Okay. Now we get to the incredible power of randomness. So let's now say they are willing to execute a randomized procedure. So this means like Alice say might make some random choice or choices, and based on her random choice, she will decide what information to send to Bob, and then Bob will use that information to output either like, yes, I think we do have the same vector, they're equal, or no, I think we do not have the same vector, they're not equal. And so they're willing to execute a randomized algorithm and output the wrong answer with at most some tiny probability. Okay, let's say at most 2 to the minus 80. So they're willing to have some really small chance of making a mistake, but they really want that probability that they make a mistake to be like really, really small. Like 2 to the minus 80 is pretty small. You could even ask for it to be smaller. Like the cost of this protocol that I'm going to show you grow, like very, very slowly with this probability. So they easily could make it, 2 to the minus 160 or something. So they could actually do this generically just by repeating the protocol twice, for example. So by doubling the cost, they can square the probability of error. Anyway, so in summary, we're going to see like just a really, really efficient protocol that is almost as good as a deterministic solution, in the sense that they can make the probability that they output the wrong answer like so tiny that it'd be like you're more likely to die from a cosmic ray killing you or something than they are to output the wrong answer. Okay, so here is how they're going to do it. So Alice, oh sorry, maybe I should mention they will be able to do this. So they'll be able to reduce the communication if they're willing to have this really, really tiny probability of outputting the wrong answer. They'll be able to reduce the communication from n field elements all the way down to 2. So just a massive, massive improvement in performance. If n is 1 trillion, they're cutting terabytes of data down to, I don't know, if our field has size like, 2 to the 127, they're cutting it down to, I don't know, like under 20 bytes. They're going from terabytes down to like 20 bytes. something like that. This will require, I'll tell you the one caveat now. This will require that the field they work over have size bigger than the length of their vectors. Okay, so this protocol won't work if the field that their vectors have entries from is too small. But again, if your field has size, for example, 2 to the 127 minus 1, well, no one has files bigger than about 2 to the 50 or something out there today. So, this field size is way bigger than this field size. This is a petabyte of data, 2 to the 50. 2 to the 60 is like an exabyte. So 2 to the 127 is just an insane amount. Like, that's more data probably than exists in the entire universe, or I don't quite know, but it's a field of size 2 to the 127 is more than big enough to satisfy this requirement. Yeah. Okay.
Can I have a question, please?
Please, yeah.
You're talking you're saying that we want to optimize the bandwidth, but don't we want to optimize like over the whole computation? Or what I'm asking is, why wouldn't hashing the files work?
Yeah, so effectively that we are going to do that. So you just sort of predicted the protocol. So I'll actually describe it in that language right now. Alice will essentially just send to Bob, sorry, we're calling them A and B. She'll send to Bob a hash of A, and Bob will just check, does H of A equal H of B? And if so, he'll output equal. And if not, he'll output not equal. But to explain the correctness of this protocol, I'd have to tell you a little bit more about how the hash function is chosen. Because for any fixed H, right, there will be some A's and B's that collide under H. So that is A does not equal B, but H of A equals H of B. And this is exactly when they make an error, is if there's a hash collision. So A and B are not the same, but once you hash them, they look the same. So I have to explain how H is chosen so that this sort of situation happens for any fixed A and B with tiny probability. We need this collision situation to be extraordinarily unlikely. But other than that, the answer is that is exactly what we do.
Okay, thank you.
Yeah. Okay. And this sort of technique is called fingerprinting. With the rough idea being that a fingerprint is like sort of an almost unique identifier of a person. So, if you scan your fingerprint out there, there could be someone else out there in the world that the scanner thinks has the same fingerprints. But it's pretty unlikely is sort of the idea. And so this hash of A, hash of B, you're thinking of this hash as like a fingerprint of A. So, we need that with overwhelming probability, for any two individuals out there in the world with overwhelming probability, they won't have the same fingerprint. That's what we need from our hash. Okay. So I will now tell you what the hash function A is. The hash function H is. It's kind of a funny hash function, but it's exactly the hash function that comes up in snarks over and over again. After today, we won't actually use the term hash function for it because in cryptography, hash function is used to refer to cryptographic hashes like SHA-256 or Blake3 or something. The hash function H here does not have to be a cryptographic hash. Okay. It's really it's not important that in this context that like for example collisions be intractable to find or something, right? So cryptographic hashes they have to satisfy properties like they're collision resistant, meaning it is intractable, like it requires enormous computing power to find A and B that collide under the hash. And we don't need that property here because A and B, are Alice and Bob's input. It's they're just fixed, and they can choose H at random. So there's no adversary here that's able to, for a cryptographic hash to be relevant, it'd have to be the case that like Alice and Bob choose H in advance, and then the adversary gets to choose A and B, to try to trick them. In that setting, they would need to use a cryptographic hash to prevent the adversary from being able to trick them. But that's not the setting we're considering here. We're saying A and B are fixed, and then Alice and Bob themselves get to choose H after A and B are fixed. So there's no one who's going to try to adversarially, select A and B to collide under H. So there's a footnote in the book about this because people have gotten confused in the past about, why the hash function, and I describe in the book and I'm about to tell you about now, doesn't look anything like the hash functions they're used to, because many readers have cryptography experience. They're used to like SHA-256, and this is just a setting where you don't need cryptography at all, and hence your hash functions can be vastly simpler, faster to evaluate. Okay, so now I'm going to tell you what H is. Okay, so here's H. Alice interprets her vector A as a degree n-1 polynomial. Okay, so this is, there are actually a number of ways to interpret a vector of length n as a degree n-1 polynomial, but I think the most natural and straightforward is to just think of the vector as the coefficients of the polynomial. So let me call the polynomial PA, P sub A. And so that polynomial is just you sum over the coefficients of A, the entries of A, and they're just the coefficients of the polynomial. And then what she's going to do is she picks AIs, they're elements of the field. So she a field element R at random. Okay. And she sends to Bob okay. And you think of R as specifying the hash function H in my notation above when I express the protocol in terms of hashing. And PA of R as H of A. So that's why it's a little funny to think of this as a hash function. It's like the random field elements that you evaluate the polynomial at, like, is the hash function. So the hash of the vector A is the polynomial corresponding to A evaluated at the random point R. So R specifies the hash function, and PA of R is the hash of A. Okay, so then Bob, just compares PA of R to PB of R. That is, he interprets his own input as a polynomial, and outputs equal if they agree, and outputs not equal otherwise. Okay, so, and this hash function, looks nothing like a cryptographic hash, right? It's like trivial to find collisions in this hash function. Like you give me any two polynomials, PA and PB, and it's not actually hard to find a point where they collide, right? So maybe here's PA and here's PB, and here are 2 points where they collide, right? And like or 3 points where they collide, and you can just sort of look at these polynomials and sort of quickly figure out where they collide. Yeah, so that would be, so that what I just said is given, with this choice of hash function, given two vectors A and B, it's easy to find an H such that H of A equals H of B. That's what this picture is, and sort of the reverse is also true. Once I tell you H, which really in this protocol would be the random field element R, it's also easy to find two vectors A and B such that H of A equals H of B, because that's just equivalent to finding two distinct polynomials that agree at the point R, right? So I just say, if I say this is R, then I just come up with any two polynomials that agree at that point. You can even have them be degree 1, right? Like just find two lines that intersect at R, and you've found a collision for this hash function. So this is not at all a cryptographic hash function, but it suffices for what Alice and Bob need, again, because there's no adversary who is able to choose A and B in a manner that depends on R, right? They're choosing R themselves at random. And similarly, there's no adversary who can choose R adversarially to depend on A and B, right? Again, they are choosing it themselves at random. So they don't need a cryptographic hash. Okay, so hopefully the protocol makes sense, right? So Alice just sent to Bob R and PA of R. So that's just, each of these is a field element. So it's just two field elements. So very efficient protocol. And the key claim, I'm going to return to the cost of the protocol in a second. But the key claim is that if A equals B, then Bob always outputs equal. That is, he outputs equal for any choice that Alice makes for R. While if A does not equal B, then Bob outputs equal with probability. So that would be a mistake for him to output equal now, with probability at most n-1 over the size of the field. Right, so that's why I said we're going to need the field to be substantially bigger than n, because we want this probability to be small. So if the field was smaller than n, then this is, like a completely trivial statement, right? There's no interesting guarantee because this is, probability would be 1 or greater. But if n is 2 to the 40 and the field size is 2 to the 127 minus 1, then this probability is at most like 2 to the minus 87, which is like really, really small. Okay. So I'm going to prove this claim in a moment. Let me just come back to the cost of the protocol. So I want to point out why we're working over a finite field here. So you might say, hey, just this is a polynomial. Why does it have to be a polynomial over a finite field? Just, interpret the entries of Alice's vector as integers, and have her send to Bob the integer PA of R. And that would work, but the problem is that working over the integers, PA of R can be certainly bigger, at least as big as R to the n-1, right? Just because, the last term in the polynomial is, a n-1 times x to the n-1. So if you evaluate just that term alone at R, you can certainly get out R to the n-1, even if the last entry of the vector is just 1. And this is a huge number. I mean, even if R is just 2, say, imagine R was 2. So they sort of picked, one of the smallest possible integers, as Alice picked that as her sort of random number. And n is 2 to the 40. Then R to the n-1 would be 2 to the 2 to the 40. And so like even writing down this number would be like a terabyte of data or something. This is a 2 to the 40 bit number then. right? So that is the number of zeros and ones required just to sort of express this number. Sorry, R is 2. Sorry, it's P. If R is 2, then P of R would be 2 to the 2 to the 40. So just writing down like the natural representation of that number is so much data that just sending PA of R from Alice to Bob is almost as expensive as Alice just sending her whole vector to Bob. So the point of working over a finite field is that these giant integers that like arise when Alice goes to evaluate this polynomial at a point don't get so giant, right? So rather than sending a terabyte of data to Bob, if we're working mod 2 to the 127 minus 1, then R itself is just R is a 127-bit number, right? That is with 127 zeros and ones, you can uniquely identify any field elements if the field has size 2 to the 127 minus 1, and PA of R is also a 127-bit number. So rather than, if we worked over the integers, again, Alice would have to send like a terabyte of data to Bob if her file is, a few terabytes in length. But by working over, even a pretty big field, 127 bits or something, Alice only winds up sending, under 256 bits to Bob or something like that. So I saw actually a few weeks ago, there was like a Twitter conversation. People were discussing like, why do snarks work over finite fields? And I didn't jump into the conversation, but this would be my basic answer is, the techniques that snarks use, they involve these polynomials and, the verifier winds up checking whether certain polynomials evaluate to this exactly the same thing at a given point. And if you didn't define those polynomials over finite fields, the numbers involved would just get astronomically big, so big that, you would just lose succinctness completely. Like just writing down one of those numbers would be like as big as the circuit that the prover is claiming to have correctly evaluated on some witness or something. I actually think it's like an interesting direction, like research direction, to understand just how fundamental is it to have to work over finite fields? Like, is this just like the current techniques sort of are only amenable to finite fields, and there might be some totally different techniques that don't go through finite fields? I guess that this isn't totally understood. I don't know exactly what you could hope to show formally, but I think that's certainly the basic answer. Why do snarks use finite fields? It's just because they involve polynomials of sufficiently high degree often that if you didn't reduce everything modulo some reasonably large prime, the size of the integers involved would just get insane. So that even writing down one of those integers would not be succinct anymore. Okay, does anyone want to ask a question now? Sort of been talking without a break for a while.
Sure. Just one question on that particular vein is I'm also looking at the MOOC, the ZK Learning MOOC, and I think I remember in there something. Maybe it was actually a lecture that you were giving about how like multivariate polynomial commitments are often used because of this like problem with the high degrees. Does this mean that you wouldn't? I mean, if the idea is that you have these like really high degree polynomials and that's why you work over a finite field, is it true to say that a multivariate like polynomial commitment wouldn't need to work over a finite field, or is that a silly thing to say?
Yeah, no. So this is a great question, really insightful. With the multivariate techniques, the degree turns out to be about, would be in this case like log n. And it's still the case that R to the log n is still too big. But it's not nearly as bad as R to the n. So stuff gets better, but still not good enough. You'd still want to work over a finite field. So this would be, like the number of bits taken to write this number down is like log n times log R. And we'd rather it be something like order log n. and basically get rid of that log R factor. And that's what working over a finite field gives you. Like you can basically, roughly speaking, choose the field to be of size, polynomial in n, that is n to some constant power, and then the number of bits needed to write down a field element is some constant times log n. Whereas if to get the security good enough, R would have to be sufficiently big that you shouldn't think of log R as a constant. This would be super, super constant. Yeah, so it's a great question. Because the degree of multivariate polynomials can be lower than the univariate ones, this issue gets less bad, but it's still bad enough you would still want to work over finite field.
Okay, thank you.
Mm-hmm. Yeah, great question. And by the way, there's an exercise in the book that asks you to give a variant to this protocol where Alice and Bob interpret their vectors not as univariate polynomials, but as multivariate ones. And you actually see that the failure probability does get better. So you could work over a smaller field as a result. So the failure probability, rather than being n-1 over f, turns into something like log n over f. If using multivariate. If you use what's called multilinear, that's a multivariate kind of polynomial instead of univariate. So even in this setting, where this very simple protocol I just described, where there is no prover, multivariate techniques do buy you something that you can work over a smaller field. Yeah. Any other questions?
So this relates to, I don't know if this is getting ahead or not. So one thing that's mentioned in the book is when you formulate the encoding as a polynomial, you use the Lagrange interpolation, excuse me. And one of the things that's mentioned is that the LDE and Reed-Solomon encoding differ in the correspondence. That the LDE is interpreted as the coefficients of the polynomial, while the Reed-Solomon is interpreted as the evaluations of the polynomial of the inputs you give it. I might actually have that backwards, excuse me. But I was just wondering if you could talk about that correspondence a bit more, because I know the book kind of goes in and talks about how they kind of represent one and the same, but it's like a technicality. And I was just wondering if you could elaborate more on that.
Yeah, so I can. Are you able to stay for 10 more minutes? Can I return to that right after I finish proving the claim?
Absolutely. I was just curious.
Yeah, no, I do want to talk about that more. It is actually an important sort of subtlety. So I will do that as soon as I prove this claim and finish up the analysis of this communication protocol. Sound good?
Sounds great.
All right, cool. Okay, so I will prove the claim, and then we'll discuss low degree extensions versus Reed-Solomon encodings. And feel free again to jump in with questions at any point. But yeah, so for proving this claim, let me just erase some of this stuff. Okay. All right. So the first part of the claim, that if A equals B, then Bob always outputs equal. That should be pretty obvious. Like if A equals B, then PA and PB are the same polynomial. Right, and then so if you take the same polynomial and you evaluate it at the same point, you obviously get out the same thing. Right? So another way of saying that is, if you take your own fingerprint twice, you're going to get the same thing out each time. So that is clear. So if A equals B, then Alice and Bob always output the correct answer. So the only situation where they might output the wrong answer is if A does not equal B. Okay, and then the claim that they, have to get really unlucky to output the wrong answer follows from a simple fact about univariate polynomials. So that is if P and Q are 2 degree n-1 polynomials, and they're not the same polynomial, okay, then they can agree at most, I think it's n-1 points. And what I mean by that is P of x equals Q of x for at most n-1 values of x. Okay. So I will explain why that fact is true in a second, but the claim like follows immediately from the fact, because if A does not equal B, then P sub A and P sub B are not the same polynomial, right? They differ in at least one coefficient. And then Alice, picks a random input R and checks whether these two distinct polynomials agree at R. And this fact says they can only agree at most n-1 values, but R is chosen at random from the whole field. So the probability that R is one of the at most n-1 values at which they agree, PA of R equals PB of R, is at most the number of such values, which is n-1, over the size of the set from which R was chosen, which is the size of the field. So that's the claim. That's the proof of the claim from the fact. This fact is just a reformulation of the fact that any degree n-1 polynomial has at most n-1 roots. Maybe I'll call this polynomial, let me give it a different name. I don't know, S. So this is probably a fact that you learned, I guess, in algebra 2 or something, middle school or high school or something. I don't know, you can always write, at least over an algebraically closed field, you can always write a polynomial as a product of its roots. I is a root of P of x minus I, right? So like this factor ensures that P of I is 0 because I minus I spits out 0 and 0 kills the whole product. So this sort of tells you that every time you add an extra root to P, you add an extra term to the product, which increases the degree of the resulting polynomial by 1. Anyway, so hopefully this is not news to anyone that any degree n-1 polynomial has at most n-1 roots. And then, so what's happening, this fact is equivalent to this fact applied to the difference P minus Q. I should have said any non-zero degree n-1 polynomial has at most n-1 roots. Obviously, the polynomial of degree 0, that's just 0. Everything's a root, but that's the only low degree polynomial with many roots. So if P and Q are 2 degree n-1 polynomials and they're not the same polynomial, then P minus Q is a non-zero polynomial that also has degree n-1. And any point where P and Q agree is a root of their difference P minus Q. So the fact that P minus Q has degree n-1 means it can have at most n-1 roots, which means P and Q can agree at most n-1 points. Okay, so that is the incredible randomized protocol that we saw today that reduced the communication cost, by allowing a tiny probability of error. It reduced the communication cost from n field elements all the way down to 2 field elements. And all we required was that the field was big enough so that this failure probability was small. All right, so that is the main topic for today. And I will now talk about low degree extension codes versus Reed-Solomon encodes, and I'll explain how to view the protocol we just saw in the framework of Reed-Solomon codes. But this content is not really essential, I'd say, for continuing in the study group. So anyone who needs to drop off shouldn't feel bad about it. Okay, so please interrupt if you want to ask something else, but I will now start talking about how to view this protocol through the lens of coding theory. And that's going to lead me to talk about Reed-Solomon versus low degree extensions as requested. Okay, yeah, please go ahead.
Maybe a quick question. I'm used to thinking about polynomials like in terms of real numbers or complex numbers. But here we are talking in context of like finite fields, and like my question is whether all the like fundamental theorems about the polynomials hold also over finite fields, or if there are some caveats.
Yeah, I mean, I think any of the results that we need for snark design work over both of them just about. You think? Yeah, I mean, we need almost nothing about polynomials in snark design except for this fact right here. Like even the snarks that use multivariate polynomials, ultimately, their security analysis ultimately relies on this fact about univariate polynomials for the most part. So this simple fact right here, that any degree n-1 n-1 univariate polynomial has at most n-1 roots, unless it's a zero polynomial, is already enough for the vast majority of snark design. I'd say there is some of the snarks that use univariate polynomials need to deal with roots of unity over finite fields. So that like an nth root of unity is like a root of the polynomial x to the n-1 equals 0, right? It's just like you raise x to some power and you get out 1. And these actually behave a lot like the complex roots of unity. And we're really only going to need to discuss this thing when we talk about Fry. And yeah, even again, you can, as long as you have in your head like the complex numbers, it's still the way you're thinking about things will still pretty much make sense. I actually happen to be recording my second lecture for this MOOC, zklearning.org, today. So it should get posted within a week or so. And it will discuss exactly these sorts of issues. Just if you're curious to see a discussion of this sooner rather than later, because this study group won't get to this for a while. But yeah, basically for now, and actually for the most part, indefinitely, this is really the only fact you need to know about polynomials over finite fields.
Thank you.
All right. Okay, so I'm now going to just sort of reformulate the protocol that we saw today in terms of Reed-Solomon codes. I'll tell you what a Reed-Solomon code is shortly. So think of Alice. Remember, Alice interpreted her vector A, which had length n. She interpreted it as a polynomial p sub a. And I want to now think of that polynomial as a much longer vector. Say it has one entry for every field element. Okay, and specifically this vector, I want to think of as just the evaluation table of p sub a. So p sub a is 0, p sub a is 1, all the way up to p sub a of, if we're working over prime field p, p minus 1. So vastly bigger vector. Think of this length as at most 2 to the 40 or something, and whereas this is like 2 to the 127 minus 1. Now note this vector is so long then that nobody would ever have time to like write down every entry of it. Okay, but what Alice does, so Bob, by the way, does the same thing. He sort of replaces B with this much longer vector, the evaluation table of PB. Sorry, I didn't mean R there, just PB. So contains all, field size evaluations of PB. And what Alice does is she says, hey, I'm going to ignore all of this giant vector PA except for the rth entry. And what I'm going to send to Bob is just R and that entry of the vector, of the encoded vector EA of R. And Bob just compares that one entry of Alice's vector, which she sent him, to the corresponding entry of his vector and sees if they're equal. Okay, so another way of saying this is that Alice and Bob check equality of a single entry randomly chosen of the Reed-Solomon encodings of their vectors of, so let me just say, I don't know, Reed-Solomon encoding of A and Reed-Solomon encoding of B. Okay. So that's a way to view what they did in terms of the Reed-Solomon code. So all I did was I said, they're implicitly replacing their vectors with, these redundantly encoded versions of their vectors, and just checking that the encodings are equal at a single randomly chosen entry. And what's happening is that the Reed-Solomon code is what I call a distance amplifying code. Okay, so that means if A and B differ in even one entry, their Reed-Solomon encodings will differ at almost all entries. So RS encoding of A differs from RS encoding of B at a 1 minus n minus 1 over, field size fraction of entries. So they sort of blow up very tiny differences into huge, easily detectable differences. So, a single entry differing between A and B mean that, the Reed-Solomon encodings differ at almost all the entries, and hence it's enough for them to compare just a single randomly selected entry of the encodings, unless they happen to pick one of the few entries at which the two encodings happen to agree, they're going to detect the difference. Okay, so that is a coding theoretic view of the protocol we just saw. So let me now talk about exactly, finally, the question I was asked a while back, which is Reed-Solomon encoding versus low-degree extension encoding. Okay, and this is getting at the fact that there are multiple different ways to interpret a vector as a polynomial. So with Reed-Solomon encoding, and by the way, not everybody uses, sometimes people refer to low degree extension encodings as Reed-Solomon encodings. And it's because they're, that's sort of what's, they do that for exactly the reason that I think led to this question and the confusion. So yeah, Reed-Solomon encoding, as I've defined it in the book, takes the entries of the vector and interprets it as the coefficients of the polynomial. So I equals 0 to 5 here of AI times x to the I. That's Reed-Solomon encoding. Low degree extension encoding, instead, C, maybe I say V0 up to V5. So it interprets the entries of the vector not as the coefficients of the polynomial, at least not in the standard monomial basis, but rather as the evaluations of the polynomial over a designated set of inputs. So let's say, so PA of 0 equals V0, PA of 1 equals V1, PA of 2 equals V2, PA of 3 equals V3. Sorry to write, it takes so long to do this, but we're just about done here. Yeah, and so so like a degree 5 polynomial, can be specified via its 6 coefficients, or it could be specified via its evaluations at 6 points. And either way, uniquely specifies the polynomial. Okay, so I give you 6 coefficients. Obviously, that tells you a degree 5 polynomial. But also, if I tell you, these 6 equalities hold, there's always a unique degree 5 polynomial satisfying these equations. Okay. And so, but this polynomial is not, these two ways of interpreting a vector as a polynomial, the mapping from vectors to associated polynomials is different, right? So what the book is trying to say is like the set of all code words of all encodings is the same in both the low degree extension code and the Reed-Solomon code. The set of all code words is just the set of all evaluation tables of, in this example, would be degree 5 polynomials. So, code words and degree 5 polynomials are in one-to-one correspondence with both codes. It's just the mapping between messages in the coding theoretic language or vectors between vectors and the associated polynomial is different, right? In the Reed-Solomon code, as defined in the book, that mapping interprets the entries of the vector as the coefficients of the polynomial on the standard binomial basis. In the low degree extension code, it interprets them as the evaluations of the polynomial over some specified domain. In this case, I used 0, 1, 2, 3, 4, 5. Again, these are interpreted as field elements, by the way. So each of these is in the field. So that, of course, only makes sense as long as your field is a prime field with a prime bigger than a 5. And of course, this protocol we talked about today required the field to be of size greater than n or whatever. So this will always work out if you use a prime field of this size. Yeah, and so it turns out that what comes up the most in SNARKs is the low degree extension encoding, really almost exclusively. And the reason is, let me see if I can explain the reason intuitively. Well, okay, let me just pause here and see, does anyone want to ask a question before I try to explain why low degree extensions come up in SNARKs?
Actually, my follow-up was, what exactly is like the implementation difference? Because so like kind of what you're getting at, but that was a really good explanation. Thank you for taking the time.
Yeah, of course. It's a great question. Okay, so yeah, let's talk about that. So let's say I'm in the protocol that we saw today using the Reed-Solomon encoding, right? Alice had to compute PA of R, where we were using the Reed-Solomon encoding. PA is Reed-Solomon. So there's a very straightforward way that Alice can do that with do this in order n field operations. Right, because remember in this case, PA of R is sum over I equals 0 to n minus 1 of AI times x to the I. So that would be, now x is R. So yeah. So what she can do is, she can just maintain like a running, so she can just like make a pass over the entries of her vector. So she starts just with the first term of the sum is A0. Then she adds to it the second term of the sum, which is A1 times R. Now she has R, in her head, right? So the third term of the sum is A2 times R squared. And the point is that, from R, she can get R squared with one multiplication, R times R. And then from R squared, she can get A2 times R squared with one multiplication. And then one addition adds it to the sum, right? Then she has R squared in her head. So from R squared with one multiplication, she can get R cubed. And she can multiply that by A3 and add it to the running sum. Now she has R cubed in her head. So, from that, she can get R to the fourth with one multiplication, and you get the idea. So the total number of field operations here, like each term of the sum is just like two field mults and one field addition per term, per entry of her vector. But if she had used the low degree extension encoding, she'd have to basically identify the polynomial with that satisfies these n constraints, that evaluates to a designated value given by the first vector entry at 0, and the second vector entry at 1, and the third vector entry at 2, and so forth, and then evaluate that polynomial at R. And it's much, much, much less obvious how she can do that. Like, how does she compute this polynomial that satisfies these constraints? And there's a section of the book that explains it. So it turns out that using the low degree extension code rather than the Reed-Solomon code, Alice can still, even though it's less obvious, evaluate the associated polynomial. So now this is no longer the Reed-Solomon encoded polynomial. It's the low degree extension polynomial in order n field operations. But it's much less obvious. So the same efficiency holds up to a constant factor, but it's the algorithm is different. So there's a section of the book that discusses this, and I plan to cover that next week. But it's probably not a good idea to cover it this, 80 plus minutes in this week. But yeah, this algorithm, which is called Lagrange interpolation for univariate polynomials, it's really important in SNARKs because SNARKs like to typically use low degree extension encodings. Okay, let me see if I can give a sense of why SNARKs like to use low degree extension encodings. What's going to be the best way to do this? Okay, I'm going to describe like how a SNARK works for like a completely trivial claim. So let's say, there is a public input with just two elements, two field elements as part of the input. The verifier knows these field elements, and the verifier is like too lazy to multiply them together, but wants to know what their product is. So we got a multiplication gate. Yeah, and so, I mean, this is completely toy, like ridiculous thing to prove. It's so simple. But, the prover sends to the verifier some value y and claims that y equals x1 times x2. Okay. So in a lot of SNARKs, the prover is going to prove this as follows. It's going to be really silly, but the prover is going to cryptographically commit to a polynomial w that extends. So meaning it's the low degree extension encoding of the vector of values in the circuit. So extends the vector x1, x2, y. So what that means is it's a polynomial w, so that like w is 0 equals x1, w of 1 equals x2, and w of 2 equals y. Okay, and now checking the claim is equivalent to checking a statement about the evaluations of w. Is equivalent. So this condition here is equivalent to, the validity of the prover's claim. Okay. So by using the low degree extension encoding, the prover has sort of turned a claim about correctly evaluating a circuit to a claim about, evaluations of some polynomial that it has committed to. And so the verifier sort of just needs to check that the committed polynomial satisfies the required constraints on its evaluations. And we kind of have like amazing machinery that will let the verifier do exactly that quickly. And in general, for a general circuit, right, what you wind up with is a constraint of this form, one for each gate in the circuit. So I have a circuit here with just one multiplication gate, so there's only one constraint, capturing like correct execution of that gate. The value assigned to the output of the gate is equal to the product of the two values assigned to the inputs to the gate. But for a larger circuit, there'd be one constraint for each gate. And we just have like really cool techniques where to check very quickly whether a polynomial w satisfies a whole bunch of constraints of this form, we can sort of, the verifier can check things without actually demanding that the prover explicitly sends every single evaluation of the polynomial. It turns out like the cryptography sort of handles a lot of stuff. So the verifier winds up just needing to know like a single evaluation of the polynomial. V winds up. So V can check that the polynomial satisfies all of these constraints, only needing to know basically a single evaluation of the polynomial instead of all of the evaluations of the polynomial. So, that sounds like magic now, but it shouldn't sound as magical as it might have at the start of today, because we've seen that there are contexts where, here we reduced a claim about two giant vectors of length n, about every single one of their entries being equal. We reduced that to a claim about evaluating a single or, one polynomial for each at a random point. So we reduced the claim of about n, things to a claim about one evaluation of a polynomial. And the snark stuff is doing something very similar, where it's reducing, this polynomial satisfying a whole bunch of different constraints, one constraint per gate of the circuit, to, the value the polynomial takes at just a single randomly chosen input. So that's why low degree extensions come in. It's because we really want our polynomials their evaluations should sort of tell you the computation the prover did in its own head. And for that, we really want the mapping from vectors to polynomials to be via the low degree extension encoding rather than the Reed-Solomon encoding, right? The vectors are telling you evaluations of the polynomial, not coefficients. Okay. I don't know how much sense that made, but hopefully it was a little bit useful.
Yeah, that does make more sense in a way. Like it's more expressive of the circuit systems that they're using within the prover, I guess.
Yeah. It's just, it turns out like we can prove things about evaluations that polynomials take, but proving things about the coefficients of those polynomials, like in the standard monomial basis, is just turns out to be much less natural. It's hard to say more than that until we actually see the proof machinery later. Yeah, but going like interpreting vectors as evaluations of a polynomial is just a really useful thing in snark design, much more useful than interpreting it the vectors as coefficients of the polynomial. Okay, yeah, so I know that's it's hard to, once you see the examples, like the actual protocols, stuff gets much less abstract. Until then, I have to kind of do the best I can, and it's a little challenging for all of us. And we'll see these examples pretty soon. It won't take us that long to get to them. Okay, so I think that is everything for today. I guess I have a couple minutes if anyone wants to ask some questions, but otherwise, thank you so much for coming and staying this whole time. And I'm going to put in the chat, the reading for next week is chapter 3. If you don't have time to read it all, I think that's fine. We'll probably slow down a little bit after next week, so you can easily make it up. And yeah, I look forward to seeing you next week. Thanks again.
Thank you.
Yep.
Thank you.
Yeah,
I have a question regarding the last explanation you made. I wondered if the verifier has a way to know if the polynomial sent by the prover actually corresponds to the circuit they agree on. I don't know if this makes sense.
Yeah, it does. So in the guts of these snarks, you need to have other polynomials that somehow capture the circuit, like which gates are connected to which, and are they addition gates or multiplication gates, right? So it's not enough to, like, I wrote this constraint here in this little toy example, and the constraint involved a single multiplication because the circuit involved a single multiplication. But for like a more complicated circuit, I don't know, maybe this multiplication gate multiplies together, I don't know, these two inputs, and then some crazy thing. This is an addition gate. Yeah. So you like what stuff gets multiplied or added in what constraints depends on the wiring of the circuit. So you need to have a way of sort of capturing, you need a way to describe the constraints by polynomials themselves, kind of. It's very hard to explain without seeing the snarks, but yeah, so basically the prover will commit in these snarks, the prover commits to a polynomial that I call W up here, that sort of just assigns a value to every gate in the circuit. But then there will be other polynomials that capture the structure of the circuit. And together, those polynomials, all together capture that the value assigned to every gate in the circuit, like, correctly respects the gate by gate operation of the circuit. So you'll see something like, I don't know, there's some polynomial capturing all the addition gates, and so you see something like this. Ignore the fact I'm putting tildes over everything. Just this is purely meant to be just give you a hint of a flavor of how these things work. Yeah, so this polynomial is capturing, like, does gate A compute the sum of gates B and C? That is it an addition gate, and it's it's in wires are coming out of gates B and C, and, like, if so, then let's this expression here, the value assigned to A minus the value assigned to B plus the value C, this will be, like, equals 0 if and only if A indeed is the sum. The value assigned to A is indeed the sum of the values assigned to B and C. So you'll see stuff like this, and ultimately, what the snarks will do is, like, basically, this W polynomial, like, is the low degree extension of, like, a valid assignment of values to gate wires, like, if and only if this polynomial here, I don't know, let me call this, I don't know, G of ABC, evaluates to 0 for all ABC over some domain, some subset of the field. I don't know. Let me, again, this, yeah, I obviously can't, like, explain a whole snark in 2 minutes. But okay. So you see there are these extra polynomials capturing the circuit, but what the prover is committing to is just the polynomials that assign a value to each gate in the circuit, and together they sort of define the relevant constraints, to confirm that the committed thing is correct for the circuit.
Okay, that makes sense. Thank you.
Great. Yeah. Thanks for the question. All right.
I have a question.
Yep.
So it seems to me that the difference between Reed-Solomon and low-degree encoding is that the latter is a systematic code. So that means that, according to your book, that the low-degree encoding contains the actual message. Basically.
Yeah, that's right. So that is the low-degree extension encoding is a systematic encoding, and the Reed-Solomon encoding is not. That's completely correct. Yeah.
Does that imply the examples that you gave now about the circuits?
Yeah. I think I guess it's sort of another way of saying that. I guess what I was trying to explain before, that like, we have very good techniques for checking that evaluations of a committed polynomial satisfy certain constraints. And so we want to interpret our vectors as evaluations of polynomials instead of as coefficients. And yeah, is it saying that the code is systematic is a different way of just saying that evaluations are part of the code word, I guess, and it's and that's a nice property somehow. I'll have to think more about whether there's something formal I can say about systematic codes just being like better codes for snarks, in a more general or formal sense. Like right now, I'm just all I'm saying is that the techniques we have seem to work well with them. So I guess I'll have to get back to you. Can you make a general statement that says, well, any systematic code is good, but a non-systematic code is problematic? There are some snarks that involve not the Reed-Solomon code, but other error correcting codes. And those codes in those snarks do not have to be systematic, but it's convenient for them to be systematic. So my guess is everything I'm saying is more a matter of convenience than fundamental needs. Basically, it's possible that there is a way to sort of use the Reed-Solomon code instead of the low degree extension code in these snarks. It'd just be nastier, just grosser and maybe a little more expensive, but not asymptotically more expensive or something. So it's not really clear in my own head. But yeah, you're totally right that everything I'm saying can just be reformulated as low degree extension code being systematic and Reed-Solomon not being systematic.
Okay, thank you.
Yeah, thanks for the question. And sorry, my answer is extremely non-committal. Yeah.
Another question?
Yep.
So it seems like the whole example we went through, might as well just use SHA-256. At least for the equal. I guess we will later look at some of the algebraic properties and use them in the snarks. But for this example, it would suffice with SHA-256 or something similar. So
yeah, here's the issue with that. There are two issues. Okay, so one is performance-wise. So evaluating SHA-256 on A and B would be slower than this non-cryptographic hash we used. But it doesn't really increase the communication. So as I formulated the problem, it wouldn't really matter. The main thing is, so theorists model cryptographic hash functions as being chosen at random from some hash family. And that, but with, so the process that standardized SHA-256 and said, this is the hash we will use. Theorists modeled that process as having chosen the SHA-256 at random from some larger hash family. But once you make that choice, right, it's, so forget about that statement. Then SHA-256 is just a fixed function, right? So once it's a fixed function, once you fix SHA-256, okay, it is information theoretically, there are collisions under SHA-256. So an adversary, like choosing, that gets to choose the inputs A and B to Alice and Bob, it would take an enormous amount of time because SHA-256 is collision resistant, but collisions do exist. So given enough time, it could find A and B that this protocol would fail on. And that's, while not really a practical concern, that is a different property than the protocol we had today. Because the protocol we had today, by having Alice and Bob themselves choose the hash at random, independent of A and B, it had the property that, for any A and B with high probability over the random choice of hash, they output the correct answer. If you just use SHA-256, you wouldn't quite get that property. It'd be like, there are some A's and B's where that, that fixed hash function just messes up this protocol because A and B collide. So it's not quite the same property, but this is like pretty divorced from practice. So you're welcome to interpret my answer as like, yes, like assuming no one can find collisions in SHA-256, this would have been fine. You're welcome. Like, that's probably what I should have said to you. It's just, yeah.
Yeah, that makes sense. Thank you.
Yeah, thanks for the question. It's a good question. All righty. More questions?
Yeah, I have one more. So this is kind of a purposely kind of naive and conceptual question. So with this lower degree encoding, we allow a method for Alice and Bob to to agree or confirm information. So I guess in a very conceptual way, what exactly is missing between low degree extension and the snark? Is it just the circuit and then a cryptographic method if we want like zero knowledge? Could you just kind of like formalize, or not formalize the wrong word, just like what definitively is missing here between like low degree extension and an actual snark?
Oh yeah, I think what's happening, and let me know if I'm sort of misinterpreting the sort of explanation you're looking for. In this protocol, like Alice and Bob knew the full inputs to the problem. I mean, Alice didn't know B and Bob didn't know A, but they each knew one of the two. In a snark, the prover knows one of the inputs, the witness, and the verifier does not. So the witness is in the prover's head, but the verifier doesn't know it. Okay. And so in the snarks, in the guts of the snark, the prover winds up cryptographically committing to a low degree extension of the witness. If to kind of put the snark in, put this setting in the same footing as Alice and Bob here, the prover would have to like send the witness to the verifier, because this witness is like the input, one of the inputs to the circuit that the prover is claiming to have correctly evaluated on the witness or whatever. Once the verifier knows the witness, then it's sort of like Alice knows A, Bob knows B. There's not some like untrusted party who alone knows one of the inputs. But the problem is, as soon as the prover sends the witness to the verifier, succinctness is out the window, and so is zero knowledge. So snarks give a way for the prover to merely commit to the witness, and then prove that. So it's like it'd be like rather than Alice knowing A and Bob knowing B, it'd be like an untrusted prover committed to A, sent a commitment to A to Alice and sent a commitment to B to Bob, and then they want to run this protocol. But neither Alice knows A, neither Bob knows B. They only know commitments, to A and B. This is all very hand wavy. So to run this protocol, Alice would have to know PA of R. And essentially the polynomial commitment schemes used in snarks, that's exactly what they let the prover do, is reveal PA of R to Alice and prove that what it revealed is actually consistent with the commitment, that provide a proof of correctness of PA of R when Alice requests it. So I think that's what's missing here is in a snark, it's like Alice would have known A and Bob would have known B. Some untrusted prover would have committed to them. And then Alice would need to run this protocol. And the snarks exactly enable Alice to do that because the cryptography that the snarks use to commit to A, commit to B, exactly allow the prover to prove evaluations of the loaded.
Yeah, that actually helps. Yeah, it does. I mean, I didn't know exactly what to get out of this question. I just was kind of trying to find a way to like conceptualize exactly like where this all fits in, and that definitely helped.
Yeah. So I think this is capturing like one of the two key properties of snarks. I guess that differs from this, which is the inputs in snarks, like the witness is committed instead of known to the verifier. And the other property is just that the checks the verifier in a snark needs to do on the committed witness are just much more complicated than equality, like a single equality check. So here, Alice and Bob only care, is this vector equal to this other vector? It'd be like a super simple circuit that just takes A and B as inputs and just entry-wise checks for equality. So you just have like, n different equality checks. That's like a really simple circuit. So snarks have to handle much more complicated circuits than that. So that's like the other level of complexity in snarks. So kind of the polynomial commitment schemes are what sort of let in this context sort of handle the fact that A and B are only committed instead of known to the verifier. And then the polynomial IOP is handling the fact that the circuits we apply snarks to are way more complicated than just this little toy that just does a quality check on every entry.
Yeah, that helps a lot. I don't know if my audio cut out before I had to reconnect, but yeah, that was kind of what I was looking for in this explanation. Just trying to conceptualize where this all fit in.
Yeah, no, I think it was it's a great question, and it turns out the answer seems. I thought the answer came out a little nicer than I thought it would. So I almost wonder if there's a way to include this in the book somehow. But it might be. Yeah. I don't know if you have any thoughts on that. Let me know. It might be a little hard to. This is a nice answer to a question, but it might be hard to raise the question itself in an understandable way in the book. So. Yeah. Anyway, so thanks for the question, and I'm glad that you got something out of the response.
So like, if anyone else don't have questions, I'm wondering like how much time do you have
Right now?
Yeah.
Let me look at my calendar. Let's see. Training. Let's say go to 1:30. Yeah, okay. I'm good. I'm good for till 1:30 if if you need it.
So that's like 10 minutes.
10 minutes, yeah.
Yeah, okay. So I want to ask something like not related to this meeting, but so I'm wondering like, so they put Plankish and Fry and get CO2, but I thought like I thought like, but then you have like Dory, Orion, or Breakdown. I'm wondering if like you can combine Plankish stuff to this stuff. I don't know if it makes sense. But.
Yeah. You should be able to. So Plonkish. Okay, Plonkish refers to a kind of circuit, and Plonk is one of many proof systems that can prove statements about those circuits. So the whole point of the paper Hyperplonk is that there are other proof systems besides Plonk that can prove statements about quote Plonkish circuits. Now in both Plonk itself and Hyperplonk, in all of these proof systems, they all work. They really give a polynomial IOP, and they just combine it with any polynomial commitment scheme. And so that's what's going on in your question. You can just identify in Hyperplonk and Plonk itself a polynomial IOP, and you can combine it with any desired polynomial commitment scheme. And the only caveat is that some polynomial IOPs use multilinear polynomials, some use univariate ones. And so your polynomial commitment scheme needs to apply to the kinds of polynomials that the polynomial IOP uses. Now, to get the linear time prover properties in Breakdown and Orion, you really fundamentally do need to use a polynomial IOP that is based on multilinear polynomials. Not univariate ones, you can take Hyperplonk, and they use KZG. You can, or PST, like sort of a multilinear variant of KGG, and you can just swap out that polynomial commitment with Breakdown or Orion. And in fact, the Hyperplonk paper has a section that they call Orion Plus, that actually changes Orion to get the proof size way down, but gives up on transparency and post-quantum security. Did that all make sense?
Yes, because like, do you like remember like several weeks ago I told you about like I'm trying to think of projects and
Yeah, we talked about Nova, right?
Yeah, I was wondering like if you can do Nova on Plonkish stuff, but I think Nico from Geometry, they already done that. So I'm looking for new ideas. Like
Okay. Yeah. Sorry, go on.
Yeah, if you can combine Planck stuff with breakdown or Brian, maybe.
Yeah. So you totally like take Hyperplonk. I don't know if the implementation is public or not, but you literally can just swap out whatever polynomial commitment scheme they're using with any other multilinear polynomial commitment scheme. So if you don't like what they're using, feel free to put in Breakdown or Orion instead. Yeah.
Yeah. Okay. So this should be a candidate, or maybe something I can do.
I guess it's purely like an implementation thing, right? Because the idea is kind of, people I think understand now, like you can mix and match polynomial IOP, polynomial commitment scheme, and take it. There was a time when for there'd be another paper, paper after paper that just says, well, we've never combined this polynomial IOP with this polynomial commitment scheme before, so we combined them and like here are the results, right? Like 3 years ago, there was paper after paper that was like this, and I think the community is past that now. So this is like of that flavor, but it's still a nice project. It's just it's an implementation task. Yeah.
I'm just like trying to get ideas, and another thing is like so I don't think I saw anyone like implement the extractors.
Oh, that's interesting. So those extractors are really just used in the security analysis.
Yeah.
I don't. I mean, no one ever, really intend to run them in the real world. That doesn't mean it wouldn't be interesting to implement one. Yeah, I don't know. Maybe that'd be cool.
Yeah. Okay. Then this can be another candidate. I don't know.
Yeah, maybe. I mean, yeah, I don't think the extractor itself like isn't useful the way the cryptographic protocol is useful, but
yeah,
it's still like just kind of a cool thing to actually implement an extractor and run it. I mean, just to do it, I guess, right? You know what I mean?
Yeah, the project doesn't need to be like purely research or purely implementation. It can be like research or implementation or research and implementation, like essentially. Okay. Thank you. Thank you
Yeah,
for the
of course. I'll let you know if I think of any other candidate projects, I guess. Yeah, but happy to provide some feedback.
thank you.
Yep.
Okay. Talk to you next week.
Yeah, sounds good. Have a great weekend.
Have a nice weekend.
You too. Bye.
Bye.